Good afternoon. This is Jason Thomas with America Makes. We're right at the start time of 2 o'clock Eastern Standard Time, so we'll begin. First off, good afternoon. I'm Jason Thomas, Project Engineer at America Makes, and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. So if during the presentation you do have a question, please submit it in the Q&A space on your WebEx screen, and I will ask it during the Q&A session. I'll do my best to get all of the questions answered. Today's webinar is on a holistic understanding of powder feedstock. Without further ado, it is my pleasure to introduce Romain Isaacs from ZEISS Industrial Metrology. Romain Isaacs, PhD, is a senior EM applications engineer at ZEISS Industrial Metrology, LLC. His primary focus is developing quality control and quality assurance solutions for metal additive manufacturing. He specializes in charged particle microscopy, including SEM, FIB, and LM microscopy applications to support the full supply chain from powder feedstock to final part certification. Romain received his PhD in materials science and engineering from the University of Maryland, where he studied the electrical properties of a novel ordered alloy using analytical electron microscopy and spectroscopy characterization techniques. Romain, I will now turn it over to you and your team.
Thanks, Jason. I'd also like to welcome everyone to today's webinar. I'd like to start by giving an overview about why we want to characterize additive manufactured powder. And I'll talk about 3 different powder characterization techniques and then show a couple of case studies. So in the AM process workflow, the quality of the final part is determined by several factors, including the material, the part design, the build layout, process parameters, and post-processing. And we can think about these as gears on a wheel with many teeth, and these teeth represent the complex interactions between each of these factors. When we have to strike a delicate balance between all of these properties in order to get good parts. So what happens when you receive a new batch of powder from a new supplier? Or what if you change suppliers? The first interaction that comes to mind is spreadability. Will the new powder cover the build plate as evenly, or will parts far from the recoater suffer in quality? Will the surface roughness increase and require additional post-processing? These are all costly hypotheticals, but if we can ensure that the powder is of the same quality, then we can ensure that the parts will maintain quality. And that comes down to characterizing the powder shape, size, and purity. If we think about the main steps in the powder print cycle, we can see that all the factors that affect our printing of the powder in this wheel. So while printing, we have to ensure good atmospheric control to prevent oxygen or nitrogen pickup, which could be detrimental to the mechanical properties of the part. We often recycle our powder to reduce costs, since most of the powder isn't used to make the part. And that requires us to vacuum the powder from the printer after the build and sieve out any spatter to get our desired particle size distribution. We may store the powder for some time before the next build, so we have to consider environmental control to reduce the effect of humidity on flowability. And then the powder is often topped up or blended with fresh powder before refilling for the next print. So after going through all these steps, you may see how critical it is for us to be able to characterize our powder to ensure that we have good processes. It's also clear that there are many opportunities for things to go wrong. So today I'm going to talk about 3 different ways to characterize powders for additive manufacturing using light, electron, and X-ray microscopy. So let's first start with light microscopy. The first step to getting good data is sample preparation. And what's important is that we spread our powder on a glass slide without agglomeration. We use a powder spreader where you place a substrate inside a pressurized chamber and evacuate the chamber. And then you place your powder particles on top. And when you depress the plunger, the pressure difference between the atmosphere and the chamber causes the powder particles to be pulled inside. And after a few seconds of settling, we can see a good distribution of our powder over the glass substrate. So we've developed a workflow using our software package from ZEISS called ZenCore, where we can acquire and analyze data. So let's take a look at how it works. So to image the powder, we use at least 100x magnification for good resolution and a wide coverage area. We stitch several tiles together in a mosaic with extended depth of field to get a good definition of the particle shape. And then we collect tiles. So each tile contains about 100 to 200 particles. And in an area like this with 9 tiles, we can get from 900 to 1800 particles for an image. And so we've done some experiments and we've learned that we need to collect at least 7,000 particles to get a low standard deviation when measuring our particle size distribution. So we acquire 10 sets of these in a mosaic. When we do light microscopy, we're trying to determine the powder morphology by measuring particle features like the area, diameter, circularity, and aspect ratio. Because we're trying to understand which of these characteristics or which combination of these characteristics affects the powder spreadability and the flowability. We know that ideally spherical powder particles will spread and flow better when raked during the build, but most times we don't have ideal powder. So depending on the method of atomization or your recycling stage, you may also have spherical particles with satellites, elongated particles, or spatter. So when using a light microscope, we can acquire several tiles in both refraction or transmission mode. In both cases, the particles show up dark on a light background. And once we acquire an image, we can segment the particles from the background and label each particle with an ID. Then we can create a table with the particle features such as the area, the diameter, circularity, roughness, and the aspect ratio. So most often we're interested in the particle size distribution. So we can also plot a histogram of the max ferrite diameter. And in this plot on the right, you can see that we have a distribution with a peak around 60 microns. So with just this analysis, you can tell a lot about your powder. You're probably most interested if you have a normal, bimodal, or multimodal distribution. And in this case, you can see that in addition to the peak around 60 microns, we have a lot of fines, which we may be getting through during the sieving process and could have implications for the printing parameters that we should choose. So one of the morphological features that we're particularly interested in is particle roughness. And generally, particles with spherical shapes and smoother surfaces flow easier than those with rougher surfaces and irregular shapes, because the higher surface roughness induces more interparticle friction and mechanical interlocking, which decreases flowability. So if you take a look at these particles that I have up at the top, you can probably tell that some are rougher than others. On the left, we have a virgin particle, and next to it, we have what looks like spatter. And then we have particles with more and more satellites going to the right. And satellite particles are problematic for the AM powder process because they prevent the smooth flowability and uniform powder distribution on the powder bed by the recoater in laser powder bed fusion methods, for example. And satellites are typically generated during powder fabrication by gas atomization. And they're also generated during the printing process when the powder is exposed to thermal cycling. And they typically show higher surface roughness and aspect ratio than, for example, virgin particles. So in the table below, you can see that if we compare geometric features like the diameter, roughness, and the roundness, we can see some differences between these powders. But what's curious is that if we look at the roughness for all these particles, they're about the same. And that's That's the case if we're using a traditional way of measuring particle roughness, which is to use the parameter ratio. So we decided to use a different approach. And in this approach, we're trying to measure particle roughness in a similar way to what's typically done for surface roughness. So by measuring the distance between the smooth particle surface and the convex hull, we can extract a surface roughness profile. And in this way, we can get a very different measurement of roughness for the particles. So if we look at the RA, RQ, RY, and RZ, we now have very different values that can help us classify powder into different categories. So we're measuring particle roughness in this way in our light microscopy workflow. And at first, we collect a mosaic, like I said earlier, like the image on the left here with 7,000 particles. And then we can segment the particles from the background, as you can see on the right, and calculate the features of each particle, including the particle roughness. And we can use those features to train a machine learning model to make a prediction for particle classification. So we go from the imaging to some segmentation to a prediction. And we classify powder into a few classes. We can do virgin, spatter, satellite, agglomeration, and elongated particles. At the end of the job, ZenCore generates a report which includes a histogram of the particle size distribution, cumulative plots, and the traditional D25, D50, and D90. We're also developing ways to compare several recycled powder batches. So you may want to know this kind of thing because it may have implications for the AM printing parameters that you should choose. So light microscopy gives us geometric information about our powder samples. But what options are available when you need more information about your powder batch? So at ZEISS, we have electron microscopy solutions for powder analysis. So when would you use an SEM for your powder workflow? I get asked this all the time. Well, we use it when we've reached the resolution limit of light microscopy. So that's if our powder particles are too small, or if we need to perform chemical analysis of the powder for verification of new or recycled powder. So electron microscopy particle analysis, we use our software package called SmartPI on our EVO electron microscope. And SmartPI is ZEISS's particle analysis solution. And it's a software suite that contains 3 parts. There's SmartPI for data acquisition, SmartPI Explorer for data analysis, and SmartPI Reporter for templated report generation. And SmartPI is a fully featured solution. It incorporates all the aspects of SEM control for image acquisition, it does image processing, and EDS elemental analysis for product characterization. So let me orient you to what SmartPI looks like in action. On the left, we have an image tile window with particles. The EDS spectra window is in the upper right-hand corner. And in the center, we have a general acquisition status window showing a schematic of the stub in green. Today, I have an aluminum silicon 10 magnesium powder on a stub. So I'm going to choose those elements from the periodic table. And the spectra in the upper right-hand corner will update as the radiation symbol moves around from particle to particle in the main window. After all the particles in this tile have been collected, the stage will move and acquire an image of the next tile and repeat this process. And in this way, SmartPI can automatically image a 12mm stub by dividing it into tiles and imaging sequentially. The particles are segmented from the background and classified according to size or chemistry. And what's nice is that we can monitor the stub acquisition process by looking at the green schematic of the stub in the acquisition status window. And now that we've acquired a few tiles, a few squares at the top are light green. And below the schematic in SmartPI, it will tell us how many tiles we've acquired, how much there are to go, and even the percentage of the target number of particles that we've chosen to acquire. So what are some of the benefits of SmartPI? First of all, it's simple. So SmartPI automatically and dramatically simplifies the operation. So you don't have to be a microscopy expert to get great data. You simply load your sample into the holder, and if they're predefined recipes, you can start your run. So there's intelligent particle detection. So we use sophisticated border particle staging algorithms to characterize and classify particles that are aligned across multiple fields of view. And finally, SmartPI is a fully integrated solution. So it controls both the SEM imaging and the EDS acquisition using one software program on a single PC. So it keeps the imaging, the EDS, and the EDS data together for post-processing and efficient data recall. So you see, if we start with image acquisition, but in the background, the software does the image segmentation and the image classification. So if we jump from the image acquisition to image processing, you can see that I've classified here according to size. So the smallest particles are in blue, slightly larger particles are in green, even larger particles are in purple, and the largest particles are yellow. However, it's also possible to classify by chemistry. And why would we do this? Well, we do this because having homogeneous powder is important for the AM printing process. Because during printing, we're creating the mechanical properties as we build. So we don't want variation in the raw material. The existence of any kind of contamination, such as oxide particles, will affect the mechanical properties and potentially induce weakness in the part. And we know that spatter, for example, has a different chemical composition than initial powder due to the loss of low melting point elements. For example, in Ti-6-4, there's reduction of aluminum. So to identify the chemical variation in the powder lot, you should check your powder using SEM with EDS. Now, EDS can't quantify interstitial oxygen and nitrogen or carbon pickup with EDS. But in most cases, we know the desired composition of the powder batch, and we can easily identify segregation, precipitation, or contaminants that may lead to inclusions in the final part and have a direct effect on the mechanical properties. So in this image on the right, you can see an example of elemental analysis on a powder particle with a cap. And on the left-hand side, you can see the spectra. The red curve shows a lower amount of aluminum and copper on the cap than the gray curve. And this difference in elemental concentration is due to the segregation during atomization, which isn't ideal because that can lead to inhomogeneity in the properties. So chemical analysis is important because it influences the metallic phases. The chemical composition influences those metallic phases that are created in the part. And so if we have any impurities, we get unwanted phases in the part that can have negative impact on the properties. So how do we do elemental analysis in SmartPI? So when SmartPI measures the features of each particle, it also collects the chemical information about every particle on the SEM stub. So once the run is completed, we can use SmartPI Explorer to review the data that we've collected. So we're looking at that window here on the right. And in SmartPI Explorer, we get particle image and particle images tab where we can see an image of each powder particle that's been categorized and color-coded according to its composition. So any outlier particles can easily be identified. So in this data set, we can see that most of the particles are the cyan color, and those are the aluminum, silicon, tin, magnesium powders that we expect. But we have a few orange ones that have been identified as aluminum oxide in orange. And after reviewing this data, we can even return to individual particles if the powder stub is still in the tool to confirm the classification or perform additional characterization. And this may be useful if you want to investigate the few gray colored particles that are currently unclassified. At the end of the run, we want to get a table where each particle is labeled with an ID. The particle morphological features, such as the area, perimeter, diameter, roughness, are computed and populated in this table. And SmartPI also plots a histogram showing the particle size distribution of all the particles in the data set. So we can see if we have a a normal distribution, bimodal distribution, or a lot of fines, which will of course affect our printing parameters. We can also create compact reports with all the metrics, like a histogram of the particle size distribution, box plots of effective diameter comparing different classes of powder. So here we're looking at some Ti-64 powder, and so we can also identify any contaminants. We have a table with critical morphological features that we want to track, and the standard D25, D50, D90 that's typically provided by the powder supplier. And so here we're conducting an experiment where we're studying, we're measuring from 500 to 3,000 particles to see exactly how many particles we need to measure in order to get a representative sampling. We can also report particle size distribution in a histogram and cumulative plot form for comparison of a similar data set. So the final technique that I want to talk about today is X-ray microscopy. So if you have a micro CT, you can use it to look at your AM powder. And we use a Versa 620, and we place a powder sample in a capillary tube between the source and the detector, and rotate the sample to collect different projections of the sample. And then we can reconstruct the data into a 3D volume. So with the reconstructive software, you can check your powder quality in 2D and adjust your parameters. And then you can pass it off to Zen Powder Analyzer for 3D segmentation. You can also do batch mode processing and report generation in the software. So on the left, we can see what a 3D reconstruction volume looks like. And on the right, you can see a 2D slice through the volume where we can start to see, some high density bright particles in the top image and porosity colored in green in the bottom image. Now, why is this important? We know that porosity in the powder leads to porosity in the parts, but we can't visualize this using light microscopy or electron microscopy. So XRM is our technique for visualizing this kind of defect. Here you can see some number and volume weighted frequency and cumulative plots of the same powder imaged over 7 days at different points along the capillary tube. And we can see that we have very consistent results. The D values are very consistent over this time. So XRM is a great technique for powder characterization. Now let's take a look at some case studies. At ZEISS, we work with researchers at Oak Ridge National Lab to qualify the parts using X-ray CT. And in this project, we're looking primarily for cracks in E-beam printed Inconel blades when we found some tungsten inclusions. And it's pretty easy to pick them up because they have a much higher content bulk Inconel. So we went back and we took a look at the powder that was used to build these samples, and we found these tungsten particles in the powder. And I guarantee you that if the researchers had seen this in the powder, they wouldn't have printed these blades, because it turned out to be an issue where the filament that was used in atomization was contaminating the powder. So XRM powder analysis is more than just the shape. Here we're looking at an alloy development project where the researchers at Oak Ridge National Lab are using thermodynamic models to design new aluminum alloys. And we're looking at 4 different samples with increasing alloying elements being added from left to right. And at the top, we have a 3D volume that's split into 2 regions to show low atomic contrast elements on the left and high Z contrast elements on the right of each volume. So if we take a look at the low Z region, they look pretty homogeneous. But on the right-hand side, we can see some differences in the high Z contrast region. On the leftmost image, we have a small high density particle. And in the image to the right of that, we can see 1 particle in a needle. But you can see that as we increase the alloying elements, it forms these globules and then really large needle structures. And this was an issue where the supplier did not mix the alloying elements sufficiently before atomization. and it showed up as brittle fractures in the tensile specimen. So I hope that you've seen that characterizing additive manufactured powder is a task that requires multiple techniques and length scales to do it properly. And in order to measure the particle size distribution for new or recycled powder, you can use light microscopes such as our axial imager. But if you're concerned about detecting contamination after recycling or your powder handling procedures, SEM like our EVO with SmartPI can be a useful tool to characterize your powder particles. And if you're doing alloy developments or you want to look at internal porosity of your powder, you can use our Versus 620 or for 3D reconstruction of the powder and even your final part. So once your powder quality is under control using these techniques, you can move on to the other steps in our Blue Line process. We have several quality solution centers all around the United States. And they're located close to the manufacturing facilities. And we have metrology experts that are outfitted with the full portfolio of ZEISS tools to support you. So please reach out to us. I'm located at the ZEISS Characterization Center in the Manufacturing Demonstration Facility at Oak Ridge National Lab. And we're dedicated to additive manufacturing for customer projects, data generation, and advancing additive manufacturing quality control and quality assurance. I'm open for any questions, so if you have any in the Q&A, I'm happy to answer them now. But you can also reach out to us at additive.us@zeiss.com if you want to get in touch with us. Thank you so much for your time.
All right. Thank you, Romain. That was great. We'll now, we'll now head into the Q&A session. So if you do have any questions for the presenter and you have not done so already, please go ahead and type it into the Q&A box. I do have a couple of questions here to start out with. So earlier on, when you were showing the sectioned boxes, when you talk about stitching, are you talking about overlapping those boxes?
Yeah, so we collect individual image tiles for the powder, but we do have some overlap so that we can, match just for image matching, and then we can tile those boxes together to create this large mosaic that we need, to collect up to 7,000 particles for the image processing.
Okay, thank you. All right, so let's see. Did the tungsten particle cause the crack in the turbine blade?
So that's a very interesting question. That's what we thought initially. But it turns out no, the cracks are there even in blades that don't have these tungsten carbide particles. So it was just a processing. These crack-prone alloys are pretty difficult to process, and that was a processing parameter issue. But in this case, it was just coincidental that the tungsten carbide particle was near a crack.
Okay, thank you. Hold on 1 second. I have a question here, and I'm having a hard time getting to it for some reason. Okay, when loading the glass capillary tube for XRM, can you simulate the recoating process, or do you just pour powder in?
No, we're not simulating the recoater process. We funnel the powder into the capillary tube before imaging.
Okay, thank you. All right. Let's see, got another one here. Have you ever tried cutting open a particle to directly visualize porosity?
Yeah, that's a good idea. I can probably show you what that looks like. So you could use a fib, for example, or focus ion beams to isolate a single powder particle. So on the left-hand side here, you can see the powder that's spread. And then in the middle, you can see an image where this is a tungsten carbide cobalt powder. And then on the right, you can see where we've sectioned the powder particle to visualize this porosity. So this is typically used for research projects when you're trying to develop a new alloy and you want to see how well it's going. So that's definitely an option that's available to you.
All right, thank you very much. Okay, I think we have one more here, and like I said, if anybody has questions, please get them into the Q&A. I would love to ask Romain anything that you might have for them. Is there any kind of powder that is harder to image than others? I know we have a lot of powders and new ones coming out all the time.
Yeah, that's a great question. So the e-beam powders are quite large. 60 microns and larger, up to 100 microns. Those are pretty straightforward to image in any technique. But as you start to go down to powders, for example, for binder jet, which are really, really small, you can struggle, with powders that are under 5 microns in size. In our XRM, we start to struggle with those kind of powders, but electron microscopy can definitely image all very, very small particle sizes. So it just depends on the technique that you're trying to use and what you're trying to see in those powder particles.
All right, thank you very much. All right, so I think that's all the questions we have. Like I said, if you have any questions, get them in, and I'll make sure to ask. But moving on, I think that's going to wrap up today's webinar series. I would like to once again thank Romain. That was a great presentation. If you have further questions, please reach out to him directly at additive.us@zeiss.com. There is going to be a post-webinar survey going out to all of those who participated. We do really appreciate the time that you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community. And as a reminder that if you or your organization would be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thank you very much. Everyone have a great afternoon.